Thank you all for joining us for the IVEM seminar. We have with us today Professor Wasielewski from Northwestern University in the United States. He doesn't really need an introduction, but I'll briefly go over some of the higher points of his CV anyway. He's the Claire Hamilton Hall Professor of Chemistry and Director of both the Institute for Quantum Information Research and Engineering, as well as the Center for Molecular Quantum Transduction. His alma mater is the University of Chicago, where he studied under Leon Stock before doing a postdoc at Columbia under Ronald Breslov. His research focuses on light-driven processes in molecules and materials, artificial photosynthesis, quantum information science, ultra-fast optical spectroscopy, and time-resolved EPR. And today he's going to talk to us about luminescent organic triplet diradicals as optical spin interfaces. So with that, I hand it to you, and I'm very much looking forward to this fascinating presentation.
Okay, great. It's good to be here on this bright, early, snowy morning in Chicago. This morning, I'm going to tell you a bit about our work that has transpired in the last couple of years in trying to exploit organic triplet diradicals as optical spin interfaces. The topic that we're particularly interested in for the last more than a decade now is quantum information science. And within this field, as we all know, it's usually divided into sensing, communications, and computing, but clearly computing gets the lion's share of publicity. But if you think about it, sensing and things involving molecular interactions are really the near-term application that don't require the kinds of conditions that computing is known to require. So basically, we focus on molecules in this context because molecules are particularly good at sensing other molecules. So molecules have advantages, namely structural modularity, and you can put them where you want them, which I'll come back to in a moment. Flexibility in tailoring their quantum properties. Spins are not the only property that are clearly a quantum property of molecules, and so you can utilize various combinations in this context, which is really a nice bit of flexibility. And 30 years of nanotechnology has taught us that we can build novel materials from the bottom up if needed. Some time ago now, it's almost 5 years ago now, we published this Nature Chem Reviews with 15 other colleagues who got together for a DOE-sponsored workshop, and this particular document is still a pretty good exposition of what it takes to relate molecules to the whole quantum information field. So I refer you to it. Okay, so we all know about nitrogen vacancies in diamond because they're right now the most popular spin optical interface that's used for a lot of sensing applications. From a chemist standpoint, though, if you think about what implanting a nitrogen and removing a carbon does to the diamond lattice, it essentially creates what the chemist would call a diradical anion, because even though we call it an NV center, it's technically an NV minus center. So that if one thinks about diradicals in general, one would like to emulate this. So what's special about it? Well, what's special about it is its energy level structure that comes essentially from its symmetry properties. It has a triplet ground state because it's a triplet diradical. And so that triplet ground state can be photoexcited, but the magic, if you will, for NV centers happens in the follow-up intersystem crossing event. In other words, there's a spin-selective intersystem crossing to a singlet state, a so-called shelving state, which directs population from this excited triplet state into this state, and then back to the ground state. So this selectivity results, if you continually pump the system, in polarizing the ground state T0 level of the triplet. So basically, by just doing essentially continuous irradiation with green light, you can actually get a highly spin polarized ground state. And then if you do spin manipulations on this ground state by simply executing transitions between that polarized state and the other two triplet levels, then you have the basis of a sensing element. Now, when you do that, of course, everything changes. And so the system is also luminescent, so that the triplet excited state luminescence actually occurs in the orange part of the spectrum. And so consequently, you can actually read the system out after you've done these spin manipulations by simply looking at the luminescence, essentially doing optically detected magnetic resonance. So that's a very powerful system. The problem with the system is that basically, well, it's an advantage and a problem. Basically, you can't really put the nitrogen vacancy centers easily where you want them because they're done by electron beam techniques. And so consequently, what one does is you have essentially a shotgun effect of putting these every which way, every depth within the diamond. For sensing, you want something close to the surface, which then is more sensitive to the environment. But of course, then things like their coherence time degrades if it's too close to the surface. But if they're buried too deep, they're perfectly protected and they don't sense anything. So this is an ongoing problem. So what we want to do is kind of address this problem using molecular systems. Here's our defect center again, and there are other defect centers again as well. For instance, like silicon carbide has defect centers and such, which are becoming very much strongly researched in at this time. A few years ago, Daniel Friedman's group, along with David Avshalom, proposed a chromium-4 complex that showed a very similar energy level structure to that of the NV center as well, and demonstrated that this particular molecule can also act as a spin optical interface. The only problem it has, of course, like all organometallic complexes, this one in particular is air and water sensitive. So that makes its application, you have to be a little bit more careful in how you protect the molecule. So what we thought we would do is go back historically to what people knew about how to make triplet ground state diradicals. And I'll get into this in detail in a moment, but basically we're using triple radicals that are polychlorinated and they're attached to the meta positions of a benzene ring. And so it's been known for decades that putting two radicals at the meta position of the benzene takes advantage of quantum interference effects to give you essentially a ferromagnetic ground state. In other words, a ground state that is a triplet. And so this has been known for quite a while. So we thought we might exploit this in this particular context. So what are our tasks and what we really want to do is for optically addressable qubits in this sense, we want to be able to optically initiate the ground state. We want to be able to do coherent microwave manipulation of this spin polarized ground state. We want to be able to read it out optically. And what that allows one to do ultimately, if you have highly luminescent materials, is in principle, you could go down to the single molecule level and have a single molecule sensor, if you will. And of course, this is a form of transduction. So if you had information that was encoded in your optical probe, then that might actually be transmitted to spins as well. So the idea of doing transduction with this system is quite appealing as well. Okay, so what did we actually do here? Well, it turns out that these polychlorinated triple radicals have become super popular in the last, I say 7 years or 8 years or so, simply because they are a good way to break the spin bottleneck that one encounters in organic LEDs or OLEDs. So that if you use these particular materials in OLEDs, you can, in principle, can get 100% quantum yield of luminescence as opposed to the 25% max you typically would get with a diamagnetic chromophore. And as I mentioned, and this review article really covers a huge territory of stable luminescent radicals. We attach these things to the meta positions of benzene. This is done fairly easily using palladium catalyzed cross-coupling chemistry, which I won't get into. It's fairly straightforward. And we work very closely with Joel Yuan-Zhou's group at UC San Diego to look at the theory aspects of this problem and how we can optimize the system using guidance from theory. So he was able to calculate the various states of this molecule. And importantly, what we concluded early on was that this molecule actually has a similar energy level structure than does the NV center. So the ground state is a triplet ground state, and we can photoexcite that to the triplet excited state. And from Joel's computations, we predict that there would be about a 80% spin selectivity in this particular system going over to the singlet shelving state, which would then return to the ground state. And so with that in mind, we started out to do experiments on this particular system. And as one expects, it has the typical absorption spectrum of a TTM type radical, intense band near 400 nanometers and weaker bands out near 550 or 600 nanometers. And it luminesces quite nicely. It turns out the luminescence quantum yield at room temperature is only about 1%, but that goes up to on the order of 70% at low temperature. So it's really quite luminescent at low temperature. And so what this also does is it gives us broad possibilities for both excitation wavelengths and for monitoring the emission from the system as well. So we do that as a function of time, and we get actually biphasic decay rates, two rates, about 6 nanoseconds and about 14 nanoseconds. And what we do in this particular case is we rely on transient absorption spectroscopy to kind of figure out where these are coming from. And so this next slide is the slide on nanosecond transient absorption, which shows the evolution of the transient spectra as a function of time, the kinetic fits at selected wavelengths, but the important one is the evolution associated spectra on the right side here, which show essentially the fast decay rate is the disappearance of this part of the system that is actually excited from the singlet ground state, because the singlet and triplet are very close in energy. So we can excite both. And so you get this shorter lifetime here. You get the longer lifetime from the decay of the triplet state. And importantly, what you have left over here is this 45 microsecond, very long lifetime, which is due to the return, the intersystem crossing from the lowest singlet state to the triplet ground state. And so basically, and this is all done at 85 Kelvin. So basically, it's evidence that we have intersystem crossing back to the singlet manifold, and with a long-lived S1 state, which then comes back to the triplet ground state. Okay. So what about EPR? So we do some pulse EPR on this, and the first thing we want to establish is the nature of the triplet ground state. This is done at Q band at 85 Kelvin, and these are pretty much standard transient nutation experiments. And you can see that we do get the square root of 2 relationship here, indicative of a triplet ground state, but we still have some significant intensity here at our so-called, what we would call our reference doublet state. So this is not an impurity. It turns out that the singlet triplet gap in this case is small enough that this equation that normally one uses for the nutation as a function of spin multiplicity is not strictly valid. So you get a bit of both. And in point of fact, I'll show you later, how this can actually be eliminated. What we have here is a system, though, that has approximately a 12 angstrom distance center to center between the two radicals, and I'll come back to that in a moment as well. Okay. So now, if we just look at the EPR spectrum, the ground state EPR spectrum at Q band, what you do find is a triplet ground state spectrum. The D value, the dipolar splitting, is really quite small because of the 12 angstrom distance. It's about 44 megahertz, and we can compute that as well using standard methods and get about a 44.5 megahertz coupling as well. So basically, we have a small zero field splitting in this particular case, as expected for the distance this particular radical or diradical has. Okay, so weakly coupled in the ground state. Okay, so what about relaxation times? Now, this is done in deuterated toluene, once again, as a function of temperature, similar concentrations. And you can see at about 5 Kelvin, we get T1 times that are in excess of 20 milliseconds. And that, of course, drops off as you raise the temperature. We're particularly interested in liquid nitrogen temperature. In our case, we kind of hover around 85 Kelvin typically. Also, the phase memory time, which of course we all know is related to the spin coherence time T2, levels out at about 12 microseconds, which is quite nice for such a system. And if we want to do a little benchmarking here as to our favorite temperature at 85 Kelvin, T1 would be about a half a millisecond, and TM in this case would be about 6 microseconds. Plenty of time to actually do spin manipulations. Okay, so what about which sublevel in the ground state is actually the one that might be polarized? So once again, doing X-band spectroscopy here we're doing transient EPR, in other words, laser pulse CW microwaves. And what we find is that when we do that, we get a spin polarized EPR spectrum here. And so this spin polarized spectrum can be analyzed and simulated with the same D value that we measured before. And also noting the fact that in this case, we get selective polarization of the T0 level. And so basically, this experiment shows that we are selectively populating one of those 3 triplet ground state levels. Okay. All right, so let's do some ODMR. We're going to do fluorescence detective ODMR in this particular case. And so once again, we're in 2-methyl THF, 85 Kelvin, with about a 2.8 gigahertz frequency. This is at S-band in a homemade spectrometer. And we use a low power CW laser at 405 nanometers to continuously excite the sample. And then we simply pulse the microwaves with the saturating microwave pulse periodically, and then do this and do lock-in detection, and then read out the signal. And what we get is the same spectrum. The ODMR spectrum mimics exactly at S-band the spectrum that we get from doing standard EPR detection. Note that the luminescence contrast is actually pretty small here. It's only like at maximum 0.05%. I'll come back to that in a moment. But note the fact also the signal noise is pretty good, even with this low level of contrast. All right, so basically it demonstrates we do have a spin optical interface here that we can perhaps exploit. So how are we going to make this better? I think that's really the crux of the matter here. And it turns out this is where guidance from theory gave us some important clues. For instance, the twist angle of these phenyl groups that are connected to the central benzene ring are important in the mechanism, because the mechanism of how the spin selectivity works from the excited triplet state of the system has to do with some degree of charge transfer character in the system. And when you twist the orbitals in that way, you enhance the charge transfer character of that intersystem crossing transition. And so consequently, if we can twist them a little more, we might actually be able to accentuate that as well. And so the easiest way to do this would simply be to insert a methyl group right in the middle, which adds more steric hindrance, which it did. And sure enough, it turns out that we have XRD structures of the precursor molecules. Note the fact that the precursor is simply the molecules with the CH bonds instead of the radicals here. And so both of these structures we measured, and so consequently, in the original molecule, we had a dihedral angle between these two phenols of about 32 degrees, but sticking the methyl group in between really gives us more steric encumbrance and results in about a 50-degree change. Okay, so what is that? What's the prediction? What is Hoel's computations result in? Well, in this case, the prediction is that we should have almost complete selectivity from intersystem crossing from this photoexcited triplet state level. So there should be some improvement in this particular context, simply due to this enhanced CT interaction that results in more selective intersystem crossing. Okay, once again, we can run through the gamut of observations here. Once again, here's the ground state spectrum, the fluorescence spectrum, and here are the various components. Now, note the fact that the triplet, the return of the singlet manifold back to the triplet ground state now is longer. And now there's a bigger difference between the triplet lifetime of the emission and the singlet lifetime, although the spectra are somewhat similar. Note now we have measuring the triplet ground state of this molecule. Once again, here, this is in deuterated toluene. same concentration, 85 Kelvin Q-band spectrum, you can see that the signal to noise is excellent from this triplet ground state. And note the fact that the zero field splitting now has gone down a bit. It was 44 megahertz before, now it's 38 megahertz. So the geometry of the molecules changed ever so slightly, which is to be expected when you have any kind of structural change, but we can actually exploit that in interesting ways in a minute. Once again, if we photoinitialize the triplet ground state by photoexciting it, we get this by using the same zero field splittings, we can simulate the spectrum again, and that simulation once again gives us an indication that we have a polarization of the T0 level as well in the ground state. Okay. Now, relaxation times. In this case, relaxation times have improved. At helium temperature, they're more than 30 milliseconds for T1. And now you have this interesting thing going on with regard to the methylated compound, and that is it plateaus here right around between 20 and 40 Kelvin and takes off again. It turns out that this plateauing is due to the essentially elimination or rotation of the methyl group, essentially, then off we go again. And so we get almost to 20 microseconds for the T2 time or TM time in this particular case. So it goes up considerably, which is good. Now, let's just do a purely optical experiment here where we simply optically polarize the system. So once again, we have a gated CW laser, so we can turn it on for a period of time, then wait, and then read it out with a short laser pulse. And then we use a gated PMT that looks only at the readout pulse, results of the readout pulse. Okay, so when you do that and you increase the length of the initialization pulse from 0 microseconds on out, what you find is that the photoluminescence contrast changes by almost 20%. And levels out around 250 microseconds or so. So this is really the time it takes under these conditions to polarize the ground state. And so this is a benchmark kind of measurement that shows the degree of polarization and how long it takes to get there. Now, if we then fix the length of the initialization pulse and then vary the delay between that pulse and the readout pulse, then you can get a measure of the decay of that polarization. And you can see that the interesting thing that the major decay here matches quite nicely the transient data that we got by other methodologies. So basically, we have plenty of time here to actually do some interesting experiments. So what kind of experiments can we do? Well, we can do our standard ODMR detection again. And once again, you can see here by just putting in a pi pulse somewhere in the middle of this continuous radiation of the system, we get a nice ODMR spectrum. Once again, we're doing this at S-band. If we can do a Rabi nutation experiment here again, and sure enough, what we get is nice Rabi oscillations here. All the wiggles going down on a somewhat sub-microsecond time scale. And this actually indicates that the length of our T1 pulse, or excuse me, our length of our pi over 2 pulse here is about 19 nanoseconds or so. We can do a standard Hahn echo experiment, pi over 2 pulse, pi, and then for ODMR, for those of you who are not familiar with ODMR, in a Hahn echo experiment, you're actually refocusing the spins, so you're essentially manipulating a coherence. But in order to do an optical detection properly, you need to translate that coherence into a population again. And so you rotate the magnetization back to the Z direction using pi over 2 pulse. And so consequently, that's what's the last pulse is always pi over 2. So you can see for tau 1 equals 150 nanoseconds, you'd expect the echo to occur at T2 equal to 150. And sure enough, there's the echo. And so it's a reasonably intense echo. Here's the other interesting thing. We can actually measure the TM value here too, but note the wild oscillations here. And those of you who do pulse EPR are aware of the fact that electron spin echo envelope modulation from the nuclei in the system are really very severe when you go to low frequencies. And that's what we're seeing here. We're seeing nuclear oscillations that are strongly damped in this particular system. And I'll show you another example coming up where we can eliminate this and get a pretty good TM value for this kind of system. Okay, so basically the bottom line here is we can do any kind of microwave manipulation that is kind of in the standard textbook regime of EPR, but using this optical spin interface. Okay, so what about sensing now? I have not mentioned sensing yet. I mean, this system is actually quite sensitive to environmental changes, which I think is probably the most interesting thing. Here I duplicate again, just for everybody's consideration, the Q-band EPR spectrum of the ground state of this system, and the zero phase splitting D value yields a 12.1 angstrom spin-spin distance if one assumes a point dipole approximation. Okay, so and that's 85 Kelvin again. Now, let's just do something simple. Let's not mess with the molecule. Let's actually just change the matrix. So from going from toluene D8, what we did is we actually put it in orthoterphenyl. And look what happens. Basically, in orthoterphenyl, our D value now increases to 75 megahertz. It's almost doubled. And so consequently, if one once again assumes a point dipole approximation, that means the spin-spin average distance has gone down to about 10 angstroms. So what could have happened here? Well, it's easy to imagine what might happen, and that is the angles between each of these single bonds in the system can actually change as a function of interaction with the matrix. And so it doesn't take much to redistribute the spins. So on average, the spins are a little bit closer, not the geometric distance between the radical centers as depicted in the cartoon, but actually more delocalized toward each other in this case. In this case, about 1 angstrom on either end, so to speak. So this particular system can be very sensitive to its environment, even from the standpoint of a simple measurement like zero field splittings. So that gives us some indication that the systems could be really nice for sensing applications. Okay. Last thing I'm going to talk about is what's really cool is you can actually dope these things, these molecules, these diradicals into their precursors. And their precursors are crystalline. As I mentioned before, we have X-ray structures of the precursors. And from the pictures I show here, note the fact that the precursor has no absorption in the visible spectrum. I mean, they're colorless crystals. They're nice little colorless crystals, but the diradicals are bright red. And so when you dope various percentages of the diradical into the precursor, you get a kind of pink-looking, pretty collection of crystals here. And so we can actually grow clusters of these things. We can grow single crystals. And we can do it at various dopant concentrations. And you might, and basically, you can imagine all kinds of interesting things you might be able to do with this. So I show once again the XRD of the original TTM system here with some of its parameters. The point I want to make is, the important point I want to make is that the shape and size of the precursor is essentially identical to that of the diradical dopant, so that replacement of the diradical into the lattice of the host molecule it fits really well. And so consequently, is it isomorphous replacement where everything's bang on exact? Probably not, but it's pretty close, as you'll see in a moment. Here's the PXRD of undoped, doped, and simulated PXRD from the XRD spectrum. So you just take the structure and just generate what the powder pattern should be. And note the fact that they're all the same. There's no change here. So essentially, by doping the crystal even as heavily as 1 mol%, we have not really messed with its structure in a significant way. So we get really the same PXRD in this particular case. Once again, we can look at the spectra as a function of temperature and as in particular conditions. This is this is just in toluene. Okay, so I just benchmark this in toluene, both at room temperature and at low temperature, just for the sake of argument. Okay, so this is sort of tells us what our starting point is. And now if we look at what goes on with the single crystal, and here's a picture of the single crystal, and we're doing this through a microscope, obviously, and basically we're just looking at this beautiful little single crystal, which is about 150 microns long in this case. And it turns out that if we use polarized light resolution of the fluorescence, what we find is that it has a tremendous dichroism, so that we can go back and forth. And so what that indicates is that these molecules are lined up really well in the crystal. And so consequently, the ordering in the crystal is really excellent in this particular case, as indicated by this very simple measurement. We can do time resolved photoluminescence as usual on this particular case. And this is on a powder of the crystals. In other words, grow the single crystals and then we make them into a powder. And so consequently, once again, we get the biphasic fluorescence behavior with fluorescence spectra that look fairly similar in this particular context, as one might expect. And here are just the luminescence decay curves. Once again, we can measure out at 600 or 680, and consequently, they're quite similar in that regard. Okay. Let's talk about EPR. Pulse EPR again. We're going to do Rabi notations again, or cube. So we're going to look for transient notations in this particular system. And once again, in this particular case, we get a pure signal just due to the triplet ground state. We have no indication of this mixing, simply because now there's no S naught and T naught mixing, simply because the exchange interaction is now greater than the difference between the G factors of these two guys. So basically, we've got a more well-behaved system in the crystal, which is good. Once again, we do transient EPR to figure out what the polarization of the ground state is. And so basically, here are two spectra. The black spectrum on the bottom is at 85 Kelvin, and the slightly noisier blue spectrum is at room temperature. And you can see both can be fit with identical parameters, and both indicate that we have a spin polarized ground state again with the T naught polarization. So once again, everything is behaving itself quite nicely here. This is a little bit busy, but this really summarizes the spin relaxation data as a function of temperature and as a function of dopant concentration, going from 1% down to 0.01%, and going in three temperatures, 5 Kelvin, 85, and room temperature. And the data is shown in the two graphs on the top, both the TM values on the left and the T1 values on the right. And the table summarizes what we see. And so if we go to the most dilute crystal, and of course the most dilute crystal has the diradicals isolated from each other better, so they're basically, there's no spin, or very little spin-spin interaction between them, and so you get the best performance parameters from that particular set. So at low temperature, the T1 is quite long, it's 146 milliseconds. TM is also about 7.4 microseconds. That goes down a bit, certainly a bit at 80 Kelvin. We're down at about 0.6 milliseconds for T1 and 5 but it's interesting, the TM does not go down that much. It goes down to 5 microseconds at 80. But interestingly, at room temperature, we still have a T1 that's 25 microseconds and a TM that's 2.8 microseconds. So it's even usable at room temperature in this particular case. Okay. ODMR, depending on as a function of dopant concentration, slight changes in line shape, but not greatly so. Here's simulating the I believe this is the 0.1% one. And so consequently, we can easily simulate it using the triplet parameters that I indicated earlier. So once again, and note the fact that this is now, this is at Q-band. And in fact, the experiments I'm showing you here, the ODMR experiments, are also done at Q-band. You can see it from the field axis on the left graph. All right, so let's just walk through this. Once again, this is the standard ODMR spectrum. We initialize for a while, delay, pi pulse delay, readout, and sure enough, we get a nice ODMR spectrum. And we can, of course, simulate this as well. In this particular case, we're looking at the onset of this effect and in the absence and presence of the microwave. So clearly no microwaves present, you don't get any effect. But there is a bit of a delay on the way in, and you see this actually straight line. This is not data. This is actually the limitations of the resolution here. And so you can see this thing lasts a long, long time. And in fact, how long this lasts? Well, we can do this experiment the other way and look at the decay of the effect. And it's decaying in something on the order of 120, 130 microseconds in this particular case. So it's behaving itself quite nicely in the crystal. And the important thing to note here is we try these same pulse experiments at 85 Kelvin now. We get beautiful Rabi oscillations again in this particular case by doing the transient nutation experiment. We can do the Hahn echo experiment nicely as well. Same situation. We did two different delay times. This is 200 T1 of 200 nanoseconds and T1 of 300 nanoseconds. And sure enough, you get the echo appearing just about exactly where you expect it to be. But here's the important other add-on that I mentioned before. In other words, since we're now doing this measurement at Q-band instead of S-band, we've gotten rid of essentially all of the eSeam effect, and we get a nice clean TM value here. And you can see the TM value is something on the order of 3 microseconds, which is essentially what we measured using standard EPR as well. So once again, we have good performance here in the crystal. And interestingly now, you can actually use this as a sensor of magnetic fields, because here is the luminescence contrast, and this goes up to like 2 or 2.5% now. Basically, either at room temperature or at 85 Kelvin, you get the same result. And this is in the powder on the left. On the right is a single crystal at room temperature. And you can see that it's symmetric about 0, obviously, but basically it's about a 1 full width at half max here is from the center to the edge here is about 1 millitesla. And so that correlates pretty well with essentially level crossing phenomena due to the fact that our dipolar interaction is on the order of 1 millitesla, basically, in these particular systems. So they do sense magnetic fields quite nicely. And so once again, the ability to sense things is important. So the other interesting thing about this is you can create thin films of these, not only really interesting single crystals that are thin, but you can also make films of these as well, which can then be applied in the sensing regime. So with that, I think I'm going to pretty much wrap up and just summarize and saying you can create a spin optical interface using an organic diradical. It has all the qualities that are desirable and it's similar to NV centers in diamond. You can dope these into host crystals of its diamagnetic precursor, and you can even demonstrate a spin optical or optical spin interface at 294 Kelvin room temperature. And I think one of the important things I want to highlight here is that theory provides important molecular design guidance for enhancing the performance of these systems. And thus far, using a high level of electronic structure theory has been giving really good results in a predictive manner that we can actually use to improve the performance of this type of system. So with that, I'm going to wrap up and thank the people who are directly involved here. I've already mentioned Professor Yuan Zhou and his really talented student, Yongrui Po at UC San Diego. In my group, Sebastian Kopp did many of these experiments. In the molecules, the diradicals were largely made by Shunta Nakamura, who's now back in Japan at an assistant professorship. Matt Krasaniak is my EPR research professor who runs the EPR lab in my group. Kate Pinekoffer and Sam Tyndall were responsible for some of the crystal fluorescence work, as well as Georgia Mantell. John Palmer also did a lot of the EPR on the single crystals, and Ryan Young is my ultra-fast guru in the group, who is also a research professor in the group. And so DOE paid for the paid for the experiments, and happy to answer any questions. Thank you very much.
Thank you very much for the presentation. I see a lot of hands, a lot of applause. The floor is open for questions. You're welcome to unmute your microphone and go ahead and ask. There's a few more participants than usual here, so if it gets a bit unruly, we can start hand raising. Let's start by just trying the free for all. Don't see any questions yet, but maybe I can start the discussion. You showed a lot of relaxation data, but in the context of quantum computing or actually doing calculations with manipulatable spins, I always have this question in mind: how long is too long?
Well, actually, too long is you need some sort of refresh rate. In other words, if you're going to do any kind of computation, you have to be long enough to get a meaningful result and read it out and then repeat it, because basically what you're doing is you're averaging, just like you would in a spectroscopy experiment. And so the only way you get accurate results is by and removing errors is by repetition at this point. There are other ways that one can do this, but you don't want to be too long, because then the repetition rate becomes a limiting factor. But I want to highlight again, though, that I think computation is probably the last most challenging application that one would consider in this context. Even communication is easier, because it turns out that nanoscale communication between processors that do computation on chip would benefit from molecular systems that actually could coherently transmit information over even nanometers to a few tens of nanometers. So sure, yeah, there's a place for molecules there as well. In computation, I think there are more challenges.
Yeah, sure, absolutely. I see a hand raised. Murgazan, please go ahead.
It's a great talk. I really enjoyed. Okay. So my question is, it's a general question. So now you are connecting the two radicals through the benzene ring. Is it possible? Can we go for one more radical to connect with the benzene ring so that we can enhance the ground state into S is equal to 3/2?
In other words, putting a third radical on there?
Yeah.
Yeah, that's relatively easy to do. Yeah, you get a quartet ground state then. I mean, we've explored quartet ground states in other contexts using photoexcited chromophores attached to stable radicals, and this has been an activity that many other groups have also engaged in. And you can generate quartet states that, but the challenge then is, can you create an optical spin interface from that kind of quartet state? And in this case, probably yes. In the other cases, sometimes.
So then one more question is means in that radical benzene ring, you can see only 2 chlorine atoms. In case if we replace even other protons in the ring with some other chlorine atoms, perchloro, some kind of stuff like that.
Yeah, actually, it turns out you want two things. You want steric hindrance there that protects the radical center, but you don't want a group there that would be reactive. Like, for instance, you could get the same degree of steric hindrance if you had 2 orthomethyl groups there, but over time, the radical center would abstract one of those hydrogen atoms. It doesn't happen fast, but it happens. And so the system sort of degrades over time.
Oh, okay. Thank you.
So you need something inert, something big, but something inert. And the easiest thing to be big and inert is a halogen. The same thing has been tried with the 2,4,6 tribromo, which also works. But bromos are a little more labile in general, so the chloros seem to be the happy medium here.
Yeah. Thank you. Thank you.
Other questions for the speaker?
I'm Roberta. Sorry, I don't know if I should raise my hand.
I'm sorry.
Please.
Can I go ahead?
Yeah.
Okay. Mike, I have a curiosity. The great advantage is that, in a certain sense, we can manipulate and control the distance and interaction about the two radicals. Do you think that it will be possible to add the optical interface also to, coupled but singly addressable luminescence qubits? Do you see some interest in? Because this would be completely different from what can be done with, for instance, with nitrogen vacancies or impurities, where this type of control is not.
Roberto, I think you're right. I think in principle, you could attach these to anything you'd like that has a spin center and explore its role either as interacting in some way with that spin center and sensing what goes on there, or providing another avenue of readout of that particular spin center. So I think multi-spin, starting with this basic kind of structure, I think you could elaborate it to do that kind of experiment.
I see. Thank you.
Other questions?
I have a quick question.
Please.
Yeah, so really nice talk, Mike. So I have a question about like the potential of using these systems for vector magnetometry as well, because you did show that they were aligned, but I wasn't sure how aligned or yeah.
Yeah, no, actually it turns out that we have that we had that experiment planned. The issue is more of micro manipulation, how many axes we really need to manipulate to get the data. So we've been talking about how to do this with our current setup, because if doing it at room temperature is relatively straightforward, but doing it at low temperature is a little more challenging because of the way our cryostat works. Every time we change the angle, we would have to open it up and start over again, which is not a good way to work. You need 3-axis positioning inside the cryostat. We only have 2 axes.
I see. Yeah, no, that makes sense. And just a follow-up question on that, in terms of like the field sensitivity, have you also kind of checking, nanotesla per hertz, that sort of, yeah.
Yeah, no, we just started doing this. So basically, yeah, that's coming up. Yeah, so all that sensitivity testing is on the docket.
Okay, awesome. Thanks.
More questions? I don't see anyone. So if there are no more, I think we're okay to close here. I would say thank you to the speaker again for this wonderful presentation. Thank you for the audience giving those nice questions. We will now take a break for the winter holidays, and our next seminar will be on the 21st of January. So look out for those reminder emails and those announcements after the first of the year. Thank you.
Okay, take care, everyone. Have a good day.
Yeah, enjoy your whole day, the rest of your day, wherever you are.